Welcome to this Advanced Hire series on uncertainties. We are going to make a set of notes together that allow you to access all of the uncertainties knowledge required for Advanced Hire. We're going to work through a number of at-home experiments that allow you to put that knowledge to use and see if your skills are progressing. We'll look at precision, significant figures, attention to detail, and we'll also look at inputting data into spreadsheets and producing digital graphs to a quality that allow you to get all of those graph marks, data, uncertainty marks in your advanced hire investigation. So today, to take part in this lesson, you're going to need your jotter or some paper that you are definitely not going to lose, something to write with, and a ruler. And that's about it. I might go and get you to collect some things to measure in things, but I guarantee there'll be things that you can get pretty easily. So, pause me now, go and collect your stuff, and come back and we'll get started. Okay, so let's start with our title, and we'll just go with the obvious here, Advanced Hire Uncertainties. And my hope is here, folks, that you can just go along with me in real time, making your note along with mine. If I go too fast, just pause me, pop it back, or just keep me on pause as long as needed. But you can always just go through it at your own pace. This should be a complete lesson as if you were in the classroom. So this is not a summary note. This is from scratch to get you up to speed. So from hire, we covered two kinds of uncertainties. So in hire, we had reading uncertainties and we had random uncertainties. Now, if your uncertainty knowledge from hire isn't brilliant, if you were never really that sure of the uncertainties or you just want a refresher, there's a whole series of hire uncertainties videos just like this one already up on the channel. So feel free to go and have a look at those. It's in Data Handling and Uncertainties for Hire in a playlist. Sessions 4 and session 7 have tutorials attached, so you could always just go and have a go at those tutorials and just make sure you can do everything at higher level before we progress you on into advanced hire. If you find there are some major gaps, then please feel free to have a look at the series. You could fast forward through the bits you know and just really concentrate on the stuff that you want to refresh. So all that's there if you need it. In advanced hire, things are still pretty much the same. We have reading uncertainties and we have random uncertainties, but we now have an extra uncertainty called calibration. So all raw data is going to have a reading uncertainty, which we'll call delta R. It's going to have a calibration uncertainty called delta C. Now the calibration uncertainty is given by the manufacturer. And it's the uncertainty that describes basically the level of precision and accuracy that the manufacturer has designed this measuring device for. It's to take into account maybe wear and tear over time as well. So that's particularly, for example, there's a calibration uncertainty for wooden meter sticks to take into consideration the fact that the wood will warp slightly over time and wear away at the ends. There are calibration uncertainties for every single kind of digital meter, stated by the manufacturer, the precision and accuracy that meter has been designed for. So obviously often, the more you pay for something, the lower the calibration uncertainty, or certainly it should be the way. So you're going to have a calibration uncertainty that applies to every single measuring device exactly the same with the reading. And just like the reading, every measurement you make with that device will have the same uncertainty. So now in the top of your data table, as well as having your reading uncertainty, you can pop in your calibration uncertainty as well. Then if we process data, okay, we're going to have random uncertainties, just like we did before. Don't know why I'm now writing the word uncertainty when I didn't before. And they're going to be called now delta U. And I'm going to use that shortening just to distinguish them from the reading uncertainty. It's just been a standardized symbol that we've been using for many, many years. So we're going to have random certainty, but now guys, we're no longer going to carry forward simply the highest percentage, okay? So we are now going to have combining formulae. Okay, so we are now going to have, we have two formulae, they're in your formula sheet, that allow us to combine the uncertainties. So it's no longer just a case of finding your largest percentage and pulling that forward all the way through. Wouldn't that be lovely? No. We now have to up the ante. So reading and random are the same as they were in higher. For raw data, we're now adding in this calibration uncertainty. And when we process, when we do calculations, we're now going to have to combine our uncertainties, not just take forward larger percentages. So that's where we're heading in this series. Now, because we actually know how to use reading uncertainties and random uncertainties, we're going to go straight for a situation where we just take some data and learn how to apply our calibration uncertainty and any kind of combining of uncertainties. Okay, so we're just going to go straight for example 1 in how to use these new things. So the first thing we're going to do is just a single measurement. It's going to be a distance measurement. And I want to choose something that not everybody is going to measure the same, that's going to have maybe a little variation in it when you carry out the measurement, so that it'll have a little bit of a random uncertainty and something just kind of slightly random about it. So what I'm going to get you to measure is the length of a blade of grass. Now, if you really can't get a hold of a blade of grass, anything from nature will do. A leaf, anything, okay? Just go find something that would be different from what anybody else is measuring. We're going to set up a tiny little data table here for us to do it. So we're going to be measuring a distance. You're probably going to be measuring it with a ruler. Can't really imagine why you wouldn't. Maybe a tape measure, but it'll have exactly the same markings on it. So that means we know what our reading uncertainty is before we even begin, really. Okay, so we're going to be measuring a distance. Now, because our blade of grass is going to be quite small, we'll probably want to really think about the distance in centimetres or millimetres. Millimetres are best. If you're going to be using a really small unit, millimetres are best. So count it up in millimetres. However, because I may want to do a calculation, I can't imagine what calculation I'd want to do with a blade of grass, but because I want to try and keep things in my SI units in my title, what I can do, so I'll record my numbers in the number of millimetres, but in my title, I'm going to record it as times 10 to the minus 3 metres. And that means I can write down my numbers as millimetres, but I've changed them into metres at the top there. Now, I can also do the same for my reading uncertainty. So as we know from higher, the reading uncertainty for a ruler is half the smallest division, so that's half a millimetre. 0.5 times 10 to the minus 3 metres. Okay. Now we've also got something else here, which is a calibration uncertainty. Oh wait, that should be plus or minus. Okay. We've also got our calibration uncertainty. Okay. We're going to think about that just at the end. So we might add it at the top here, or we might put it down the bottom, but we'll just think about the calibration towards the end when we're combining our uncertainties. So we're going to measure our blade of grass 5 times, which is the minimum number of repeats for advanced higher, minimum. We tend to do 6 repeats as a standard, just so you're over and above the minimum, which is always safe. We're going to do 5 today. So we'll have our mean value, then our random uncertainty, and now we're going to add on an extra final column, which is going to be for our overall uncertainty in the end. Okay, so I like in my data table, even if I'm going to do calculations outside of my data table, I like to have all of my final values in my data table so that when someone's looking at my data, they don't have to look through a whole page of random calculations just to see the final result. If they want to see how I got there, they can go and look at my calculations, but everything they want to see is right there in the data table. So you go and get your blade of grass, I'll go and get mine, and I'll see you in a few minutes. So you should pause the video now, go and get your grass, and make all your 5 recordings of your grass length. We kind of want a little bit of variation in the measurements so that your random uncertainty isn't 0. So I'm not saying fabricate that, but it's likely that you'll place the grass slightly differently each time. So don't worry about don't try to make the measurements exactly the same every time. It's probably better for this exercise that they're not. Okay, and let's just find our random uncertainty. So remember, random uncertainty is maximum measurement minus minimum measurement divided by the number of measurements to this first sig fix. It just so happens mine only has one sig fig, but your random uncertainty must only have a single significant figure. And just checking that my random uncertainty is the same number of decimal places as my mean value, and it is. And my mean value is no more precise, so no more significant figures than my raw data, which is not. Okay, now I can't complete my final uncertainty in the distance yet because I need to combine all my different kinds of uncertainties. And I've got 2 so far. I've got a reading uncertainty and I've got a random uncertainty. So far we're still in the realm of higher. Now, a standard ruler like this has a standardized calibration uncertainty that's kind of accepted for kind of industry, advanced higher, it's all fine. I'm actually, in the description of this video, I'm going to link the sheet of standard calibration uncertainties that we give out. But the calibration uncertainty for the ruler, delta C, is 0.1 millimeters. So that is plus or minus 0.1 times 10 to the minus 3 meters. Okay, so now I have my 3 forms of uncertainty, my 2 raw data uncertainties and 1 bit of process data, my random uncertainty. So I'm going to show you how we bring those together. So the first uncertainty formula in your advanced higher set of formulas, apart from the random uncertainty formula, is the combination. And in your formula sheet, it looks like this. So combining delta R, delta C, and delta U. Now, the important thing about these uncertainties, and the reason we use this particular combining formula, is they are in the same unit. So for any uncertainties in the same unit, we use the following formula. Delta W is equal to the square root of delta x squared plus delta y squared plus delta z squared. Okay, now we would always modify this formula, so that's how it looks in your formula sheet. You would always modify it to use the symbols that you're using. So we want to know the uncertainty in a distance, delta D, Okay, you could have called it length, L, doesn't matter. And we're going to be combining delta R, reading uncertainty, delta C, and delta U, the random. Okay, so let's just pop those in. So that is 0.5 squared. I'm going to leave the times 10 to the minus 3's off because we're just adding all of that onto the end. So 0.5 squared, 0.1 squared, and 0.2 squared. Yeah. Now, this brings into one of the kind of first little rules of combining uncertainties, and that's if any uncertainty is 3 times smaller than the others, it will become negligible. So I know that when I put this into my calculator, guys, this 0.1 is going to basically have no effect whatsoever. However, there's no harm in having it there. It's just showing that I'm being conscientious, but it's quite a useful rule to keep in mind that if one of your uncertainties is 3 times bigger than the others, that it is going to completely take over. And that's often really great when you come into, when you're doing your investigation, you've got loads of uncertainties hanging around, you're like, oh my goodness, I have to combine so many. And actually, if you just look carefully at them, one uncertainty will be way bigger than the others, and that actually gets rid of the entire problem for you. If one uncertainty is 3 times bigger than the others, then the others are negligible. So here, this uncertainty is negligible compared to 0.5. Now, 0.5 is not 3 times bigger than 0.2. Okay, so these two still need to definitely go into this formula, but 0.1 is pretty much going to disappear. Okay, so let's see what we get out of the calculator. In we go. 0.5 squared plus 0.1 squared plus 0.2 squared. 0 point, and we get all these numbers in our calculator, and of course, just like anything, we're going to take the first sig fig. So that is 0.5 times 10 to the minus 3 meters. And as expected, the 0.5 is just all consuming. We can see the actual uncertainty is slightly larger than that because of the 0.2, but ultimately it's not going to matter because we only take the first sig fig. So that allows us to finish off our measurement here. The distance of this blade of grass is 101.6 plus or minus 0.5, close my brackets, all times 10 to the minus 3 meters. So guys, try and have your measurement and uncertainty to the same power so that you can take the power out of the bracket. It's so much neater doing that. Just going to do our final checks. So I have a 4 sig fig final number. I have 4 sig fig raw data, so that's absolutely fine. I have a single decimal place uncertainty, and I have a single decimal place in my final answer, so that's all fine. And there we go. There's our first combining formula. That's how we combine the uncertainties of our individual measurements. So unfortunately, guys, you have to go through that process for every measurement in Advanced Higher. Trust me, you will get really quick at it. And the main thing is to get spreadsheets to do it for you. I'm just going to finish off our data table here by popping in our delta D, which was 0.5. I just want to point something out about my data table, guys. So this kind of section of data table is what your dependent variable should look like every single time, pretty much. Notice, folks, when I've divided up my mean delta U and delta D columns, I've been very careful not to go above and split them from the overall title and units, because if I do that, and it's the really, really common mistake with tables, if I separate my mean delta U and delta D with a line coming up here, what I'm basically saying is that it's not the mean of the distance and they don't have a unit. So if I separate them off, they are now not part of the distance and they are not measured in times 10 to the minus 3 meters. And of course, that's not what we want to say at all. That is definitely the mean distance. It's absolutely measured in times 10 to the minus 3 meters. And so are these two. They're all measured in the same unit. So be very careful when you're subdividing your columns that you're not separating something from its overall label and unit that you don't want to. Okay, be really careful of that, guys. It's the most common table mistake. So in our next example, we're going to look at combining the uncertainties for quantities that are not in the same unit. See you then. Thanks, folks. Make sure before starting the next video that you go and calculate all of your uncertainties and your final value with your data.